Greetings everybody. This video will hopefully explain to you how to work problem 4 of those collection of Newton's second law problems that I posted. And here's the problem. You have a hockey puck on a frozen pond and it's given an initial speed VI equals 20 meters per second, obviously in the positive x direction as shown here. The puck remains on the ice and it slides a distance of 115 meters. So that's my x. It slides a distance of 115 meters before coming to rest, meaning that after it slides that distance of x, which we know, 115 meters, it comes to a stop. So V final is 0. So I want to use this information and I want to determine the coefficient of kinetic friction. So in this case, there is friction. Even though it's ice, there is friction. I want to determine the coefficient of kinetic friction, UK, between the puck and the ice. Well, this is a problem whenever you have, for what we'll see in chapters 4, 5, and 6, whenever you have an object that's given an initial speed, and then it moves with, has some initial speed, and then it eventually comes to a stop, meaning there's obviously has to be friction. Well, in that case, these problems, you solve them using 2 steps. You have to apply Newton's second law to the moving object, and then you also have to use the one-dimensional kinematic equations. So that's very standard. We'll do another example later on where you have an object, somebody skiing down an incline, and at the bottom of the incline, it then becomes horizontal. So they ski down the incline, then they get to the horizontal, they continue skiing, but eventually they come to a stop. So in those types of problems, you have to apply Newton's second law, and you have to apply the 1D kinematic equations. Very standard technique. All right. So let's go ahead and let's draw all the forces acting on the hockey puck. Remember, there is friction because you're being asked to solve for μk, the coefficient of kinetic friction between the puck and the ice. So we know there is going to be friction. So we are going to need Fn and mg, unlike the previous example where there was no friction. All right, so let's go ahead and draw all the forces and then get the solution. So here's the hockey puck as it's sliding along the ice. It starts here with a VI of 20 meters per second, travels a distance x of 115 meters, and then comes to a stop. So right here, well, in the y direction, I have the normal force of the ice pushing on the puck. That's my Fn. I have the weight of the puck, which is mg, which is the negative y direction. Now, obviously, because the puck is not accelerating in the y direction, it's only accelerating in the x direction. And the only 2 forces in the y direction acting on the puck are Fn and mg. Obviously, Fn has to equal mg. Nothing complicated about that. There's no acceleration in the y direction. Fn and mg are the only forces in the y direction. Obviously, they have to be equal. It's not complicated. So right away, I know that Fn equals mg. That's Newton's second law applied to the puck in the y direction. Okay. Well, there's one other force acting on the puck. Remember, the puck is decelerating in the positive x direction because it's slowing down. Remember, it's coming to a stop. But it's decelerating in the x direction. It's decelerating, but it's moving in the positive x direction. See, it's moving from here to V initial. It's moving in the positive x, but its acceleration is going to be negative. But because it's moving in the positive x direction, the kinetic friction force, Fk, that I've drawn here, that has to act in the negative x direction. Because the puck is moving in the positive x direction, Fk, because there's kinetic friction, because I'm asking you to solve for μk, the coefficient of kinetic friction, so Fk has to be in the negative x direction. So those are the 3 forces acting on the puck: Fn, mg, and Fk. Why is Fk in the negative x? Because the puck is moving in the positive x. Remember, friction force is always exactly opposite to the direction of the motion. And again, we know right away Fn equals mg. Okay, now let's look at the x direction. Let's apply Newton's second law in the x direction to the puck. Well, remember, sum of the forces in the x direction equals m times a. Well, the only force in the x direction is Fk, but it's negative, which is fine. So we have minus Fk. That's the only force acting in the x direction. That has to equal the mass of the puck times the acceleration. Okay. Well, now here we go. This is a good first thing. What is Fk? Fk is always mu k times Fn. Doesn't matter what the geometry is. What is Fk? Fk is always mu k times Fn. Well, what is Fn? We know Fn is mg. So now we have minus mu k mg equals ma. Well, I'm going to go ahead and solve that for mu k. Nothing complicated. I get mu k equals minus a over g. Well, hey, we're almost there, but what is a? What is that acceleration of the puck? I don't know. Well, to get that acceleration, I need to use one of the 1D kinematic equations. Okay, so we end up, we have mu k is equal to minus a over g. I don't know a. I know g, obviously. Now, to get a, I'm going to use the 1D kinematic equation. So here I'm saying let's use 1D kinematic equation 3. Well, why am I choosing that equation? Well, let's go back to the 1D kinematic equations. And here they are. These are the 4 equations, just going from in order 1, 2, 3, and 4. Well, why am I using equation 3? Well, a lot of times we can set x initial equal to 0 and just replace x final with x. So in other words, I know x, going back to my problem, I know x. Remember, x is 115 meters. That's the distance it slides before it comes to a stop. Well, I know vi. And because it comes to a stop or comes to rest, I know vf. So I know vi, I know vf, and I know x. Well, that tells me right away, and I need a, so that tells me right away, kinematic equation 3. I know vf, I know vi. In this case, I'm replacing the term in parentheses. I'm just replacing that term with x, because I'm setting xi equal to 0. And when we do that, we can just drop the subscript on the x final. So I'm saying v final squared equals v initial squared plus 2ax. I know vi, I know vf, I know x. I just need to get a. So here's kinematic equation 3. V final squared equals v initial squared plus 2ax. Well, v final squared is 0, so that term goes away. So I have 0 equals vi squared plus 2ax. Solve for a. And a is equal to, just be careful, it's minus, then parentheses vi squared all over 2x. So that's my expression for a. I'm going to take this expression for a, and I'm going to put it right in the equation for mu. I'm going to put it right in there for a. So I'm going to mu, so I have minus a over g. What I'm going to do with a, I'm replacing a with the minus vi squared over 2x. Well, the minus signs cancel, and you're going to get, in other words, don't be confused. I'm just taking this expression for a, the minus vi squared over 2x, and I'm plugging it in right there for a. Right in this equation. So and you get mu k is equal to vi squared over 2gx, because the minuses will cancel. So you have a minus, and you have a minus. The minuses will cancel, and you're going to get vi squared over 2gx. Well, vi was the 20 meters per second. G is 9.8 meters per second squared. X was 115. So plug in the numbers, and you get a coefficient of 0.177. And that's very low. and again, the friction between a hockey puck and ice, there shouldn't be a whole lot of friction. Remember, coefficients of friction are always going to be less than 1. Remember, they have no units. But again, just to summarize, this is a very common technique where it's a combination of Newton's second law, and then you have to use one or more of the 1D kinematic equations. And I'm going to go ahead and stop this video and get it posted, and we'll do another one like this involving, again, a skier sliding down an incline, sliding down a slope. Then when they get to the bottom, they're now on the horizontal, and they continue skiing, but eventually they're going to come to a stop. Right away, that tells you it's going to be Newton's second law and one or more of the 1D kinematic equations. All right, but we'll cross that bridge when we get to it. Let me go ahead and save this video and get it posted.